Hello everyone. In today's video, we think about some of the geometric features of the vectors that we've been working so far. And we'll define a couple new notions and explore their implication. The first new idea that we introduce is that of a norm. Norm is a synonym for length. So when we speak about the norm of a vector or of its length, we exactly mean the length of the segment that our arrow would be when we draw it on space on paper. Let's go and look at the technical definition. If I have a vector v, v1 through vn, its entries, then its length is given by the square root of v1 squared plus v2 squared plus dot 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 plus vn squared. You may be familiar with this notion here if you think about a vector in R2. And I take an arrow like so. By the Pythagorean theorem, the length of that arrow is the norm of the vector, is given by its x component plus its y component, and of course, squared and under a root. So what we're doing here, defining the length of a vector, is a generalization of the Pythagorean theorem in the plane. Let's have a look at these other couple examples. These are three-dimensional vector and a four-dimensional vector. When we compute their lengths, we get respectively the square root of the sum of the squares, which is 1 plus 4 plus 9. That's the square root of 14. And here for u, again, we take the square root of the sum of the squares of the components. Minus 1 squared is 1, plus 0 plus 4. So this vector has length square root of 6. The notion of norm can be useful to define the distance between two vectors, which is a generalization, again, of the distance formula that you may have seen between 2 points in the plane. Here's sort of our setup. Imagine you have two vectors, u and v, and you want to measure how far away they are from one another. We should imagine all of the vectors applied at the origin here. So the distance you want to measure is exactly the distance between the heads of the two arrows. But that is nothing but the length of the vector u minus v that you can see here. So the distance between u and v is nothing but the norm of that vector, which is given exactly by this expression here. U minus v has entries u1 minus v1, u2 minus v2, etc. You square them all, add them up, and take its square root. So if we were to look at this example where u and v are given by 1, 2, 3, and 3, 2, 1, and I were to compute the distance between them, I would have to find their difference. 3, 2, 1. This difference vector is minus 2, 0, 2. And when I take the norm of that, I get the square root of 4 plus 4. I square all the components, one of them is 0, so I get a square root of 8, which is nothing but 2 square root of 2. Okay, the next new tool that we're going to define is called the dot product, and it's defined as follows. If I have two vectors of the same dimension n, u and v, when I dot them together, what I'm doing is, let me write down maybe one next entry here, u2 and v2. What I do is I multiply the first vector of the first times the first entry of the second, and then I add to that the second entry of the first times the second entry of the second, and so on up until the bottom. So you see here that I take u1, v1, and that's the red contribution, and then I take u2, v2, that's the blue. When I get to the bottom, I'll have un, vn, which is my last summoned in here. So let's try just to compute it in this little example. what I want to do is U1 times V1, that's 1 by 1, which is, I'll leave it indicated for now. Then we have 2 times 0, those are the second entries, and then we have 3 times 5. If I add these together, I get 1 plus 0 plus 15. That's how the dot product works. Let's have a look at some properties of it. And I want to comment about one in particular, which is this first one, property A. Property A tells you that there's a relation between the norm that we just defined and the dot product. In fact, let me just write it out here. The norm of U should be the square root of the sum of the squares of its entries. So when I take the norm of U squared, I just get U1 squared plus U2 squared plus U3 squared all the way to UN squared. But if you stare at this, you realize that this is nothing but U1 U1 plus U2 U2. So this is an intermediate step that I still want to write, UN UN. That's exactly what I get when I dot the vector U with itself. So let me point out that all the other U's appearing here are entries, but this is the vector U dotted with itself. So that's our first property A. It's very important. The second one is also very important. Since U dot U is a sum of squares, just like we wrote down here, the only way that it can be 0 is that all of the squares in it are 0, because squares are positive. So as soon as one of these squares is non-zero, then U dot U is non-zero. And that's exactly what we're saying here. If U1 squared plus all the way to UN squared is equal to 0, well, the only way that that can happen is that UI is equal to 0 for all I. So this is my comment on property A, and this would be property B. The others are maybe less crucial than these two. The dot product is commutative, so U dot V is equal to V dot U. It is distributive on both sides. I can distribute the dot product on a sum, and I can factor out constants from it. And well, F and G are properties about the norm and the dot product, but they're strictly related because norms and dot product are the same. So whenever if you think for a second about property G, rescaling a vector changes its length, not by the factor that you're rescaling, but by the absolute value. If I take a vector and I multiply it by -2, the length is still multiplied by 2, not by -2. Okay. One last thing that I should point out that is very important is that we can give a different interpretation of the dot product as in terms of matrix multiplication. So it's written here. Suppose I take the dot product between U and V. By definition, it's U1 V1, U2 V2, all the way up to UN Vn. I can write that as a matrix product between the matrix U1 all the way to UN. This is a 1 by n matrix, and the matrix given by the vector V, which is an n by 1 matrix, meaning, yeah, it's a vector. So when I write it like this, it's the same, right? Because what happens here is that I would do U1 times V1, and then U2 times V2, all the way to UN times Vn. So the two expressions match, but when I write it like this, I can just write it as the matrix product between the transpose of U, which is nothing but U written as a row vector, and the vector V. Here's a little example just with numbers. If I want to think about the dot product between the vector U, 1, 2, 3, which I already transposed here, and V is 1, 0, 5, when I multiply them with matrix multiplication, I do exactly 1 times 1 plus 2 times 0 plus 3 times 5, which is 16. And that's exactly identical to what I would get if I were to dot them with one another. The reason why it's important to think about the dot product like this is the following. Suppose that you have a matrix now that enters the picture, and you have your two vectors u and v. Now, what happens to the dot product of AU dotted with v? This is not one of the ones that showed up in the properties, but this is another crucial property that we need to keep in mind. By what we just said, by the interpretation via the transposition product, this is the same as writing AU transpose V as a matrix product. But when I transpose a multiplication of a product of A times U is the same as transposing U and then transposing A and then leaving V there. So I could alternatively write this as follows, as a product of matrices. But when I write that like this, that's the same as saying that I'm dotting the vector U no longer with V, but with A transpose V. And I'll summarize that in this box over here. AU dot V is the same thing as U dot A transpose V. So some people refer to this property as the fact that you can move matrices across the dot product, but you have to transpose them. Okay. Finally, let's do some computation that will help us understand the geometric meaning of the dot product. The first idea that I want to convince you of is based on what happens when we have unit vectors. A unit vector is a vector whose norm is equal to 1. So suppose that in this picture here, U and V are unit vectors. In other words, if you think of this in the plane, you should think of the heads of U and V as points on a unit circle. If you imagine that, well then, what's going to happen to the dot product, and we'll show it in a second, is that the dot product between the two is equal to the projection of one of the vectors onto the other. It doesn't matter which you're projecting onto which, because you'll get the same answer, as you can see here, because this red segment is the same length as this blue segment. But you should think of it as that projection. And in fact, in this particular case where U and V are unit vectors, you can see that that projection is exactly the cosine of the angle theta between the vectors. In other words, in this particular setting, U dot V is equal to the cosine of the angle between U and V. That's actually a general thing. We'll get there in a second. First, let me point out a few things. I want to remind you of this property 1, which is, I guess it was property A in the table. The square of the norm of a vector is the same as dotting the vector with itself. So now I will compute the norm of the distance between U and V. And if you compute that, you see the following result. Let's just do it together. The square of the norm of U minus V is U minus V dot U minus V. I can distribute this out. So I get U dot U plus V dot V plus I have, minus V dot U, that's this mixed product, and then I have minus U dot V. So when I wrap this up, I have U dot U, which is nothing but norm of U squared, plus the norm of V squared by the same token, minus twice U dot V and V dot U are the same because the product is commutative, so I can write them as U dot V. Now, another thing that I should remind you, not from this class, but from some trigonometry or things that you may have seen before. And if you haven't, well, we're just going to say what it is the law of cosines. Whenever you have a triangle like this with edges A, B, and C, then you have the following relation between the edges. C squared, so the opposite edge to this angle theta, is given by a squared plus b squared, corrected by minus twice ab cosine of theta. So this looks like the Pythagorean theorem when theta is equal to, well, when the cosine of theta is 0. Yeah, when theta is a right angle. Theta is given by an angle of 90 degrees. In general, there's this correction term with theta, and by calling these edges length of u and length of v, and then u minus v, this difference here. So let's say that c is the norm of u minus v. The law of cosines tells us that the norm of u minus v is equal to the norm of u squared, which is a, and plus the norm of v squared, which is the length of b, minus twice ab is norm of u, norm of v, times the cosine of the angle between them. Now, let me remind you that in 2, we wrote an expression for u minus v norm squared, which had norm of u squared, norm of v squared minus 2uv. And here we wrote that norm of u minus v squared is equal to the same thing, except the last term is different. So I can set them equal to one another, and I get this chunk from 2, this left-hand side here, and the right-hand side here from number 3. So when I simplify them, these norms disappear, and then I can divide both by minus 2 to end up with the following relationship, which is the important one for us and the one that gives geometric meaning to the scalar product. The scalar product between two vectors is given by the product of their norms adjusted by the cosine of the angle between them. A simple consequence of this fact is that when the two vectors are perpendicular, perpendicular means that the angle between them is equal to 90 degrees. In other words, its cosine is equal to 0 because the cosine of 90 degrees is 0. And that's equivalent to saying by this formula up here that the dot product is equal to 0. So what we have in the plane is that two vectors are perpendicular if and only if their dot product is equal to 0. This is going to be our definition of perpendicular for the rest of the class. We say that two vectors in any dimensional space in Rn, they are orthogonal or perpendicular to one another if their dot product is equal to 0. Here's a little example of a couple vectors that will turn out to be perpendicular. If I dot them with one another, that's the same as doing the multiplication 1, 4, minus 2 times minus 8, 3, 2. And when I compute this, I get negative 8 plus 12 minus 4, and that's a 0. Orthogonal vectors. We don't know exactly how they look like, but they will make a right angle somewhere in three-dimensional space. Okay, so now we've started our discussion by building on the Pythagorean theorem in dimension 2. When we drew the plane, we used the law of cosines and we used two-dimensional things. But we can now prove the Pythagorean theorem to hold in any dimensional space. So this is a generalization of the theorem that you already know. Let's have a look at the statement. Any two vectors in Rn are perpendicular with one another, orthogonal, if and only if the following thing is true. The square of the length of the hypotenuse is equal to the sum of the squares of the edges. So the picture you should have in mind is always this. You have a vector u and a vector v, and their sum. So you can see that the length of V is the same as one of the short edges of a right triangle here. Except now you should have this picture in mind, but insert it in any dimensional space. It will always look like this and it will always work. The proof that it always works is the following. If I write down u plus v norm squared, that's the same as dotting u plus v with itself. So I get u dot u plus v dot v plus, again, like before, I should have v dot u plus u dot v. But then I can clean this up to the following expression. U dot u is norm of u squared. V dot v is norm of v squared. And this is twice u dot v because the scalar product is commutative. So you see that the quantity u plus v norm squared is equal to the quantity u squared plus v squared, norm of u squared plus norm of v squared, if and only if this amount here, 2 times u dot v is equal to 0. But then that being equal to 0 is the same as saying that u is perpendicular to v. And that's the proof of the theorem. We showed that if two vectors are perpendicular, well, that's true if and only if the two quantities highlighted here in red coincide with one another. Okay. The next video will be about more of the properties of scalar product.